Imagine you run a manufacturing plant. Your product is selling well, so the natural instinct is to make more of it. Ramp up the assembly line, crank out more units, and watch the profits grow. This graph illustrates the problem with infinite scaling. As production increases, the green line showing total revenue rises. But eventually, you have to pay overtime, buy extra machinery, or secure more expensive raw materials. That causes the red line, your total cost, to curve upward sharply, eventually eating up the revenue completely. If we subtract those rising costs from the revenue, we get a single bell-shaped profit curve. Somewhere on this curve, right before the costs start accelerating too fast, there is one exact point of maximum profit. The challenge for any business is finding exactly where that highest peak sits. If you guess, you risk overproducing and losing money, or underproducing and leaving cash on the table. Instead of expensive trial and error, we can locate that perfect point by looking at the geometry of the curve itself, using a mathematical tool known as a derivative. This textbook chart shows an increasing function. As long as a graph climbs left to right, it has a positive slope, meaning values are going up. When the function starts falling, it becomes a decreasing function, and the slope turns negative. Right at the absolute highest point between climbing and falling, something specific happens. The slope completely flatlines. It forms a perfect plateau that is neither increasing nor decreasing. To find that flat spot, mathematicians use the first derivative. The first derivative acts as a compass that calculates the exact slope of a function at any given point. By taking an equation and setting its first derivative to 0, we instantly locate every flat spot, or critical point, on the entire curve. But there is a catch. The first derivative finds the flat spots, but a flat spot at the top of a hill looks exactly the same as a flat spot at the bottom of a valley. We need a second level of investigation to tell them apart. Here we see two distinct types of critical points side by side. On the right is a relative maximum, the top of our peak. On the left is a relative minimum, the floor of a valley. Both have a slope of 0. To tell them apart without drawing the graph, we use the second derivative. This tool acts as a detector that measures concavity, which is the direction the curve is bending at that exact flat spot. A negative second derivative means the graph is strictly concave, curving downward like a dome, proving it's a relative maximum. If it's positive, the graph is convex, curving upward like a bowl, proving a relative minimum. There is one more possibility. If the second derivative equals exactly 0, you found an inflection point. These graphs demonstrate inflection points, the exact mathematical locations where a curve changes from concave to convex, or vice versa. In business terms, this represents the crucial moment a company stops growing at an accelerating rate and begins to suffer diminishing returns. Combining these tools removes the guesswork from scaling. The first derivative pinpoints the flat plateaus, and the second derivative confirms exactly what kind of terrain you are standing on. Business strategists and economists rely heavily on these specific mathematical rules to run large organizations, even if they use different terminology. This text shows the translation. The first derivative of a total cost function is marginal cost, the cost of one additional unit. Similarly, the first derivative of the total revenue function is marginal revenue, the money from selling that extra unit. To find peak profit, set the profit's first derivative to 0, revealing a crucial point at 20 units. The second derivative yields negative 300. Being under 0 proves a concave curve, confirming 20 is the absolute maximum profit point. Calculus allows us to map the hidden structure of these equations. By calculating the first and second derivatives, human beings can reliably find the perfect point of efficiency in a real world constrained by limited resources.